Hi there, Calc 3 friends. It's Ben again. We're taking a look here at the idea of the integral test. This is one of the methods that we have of seeing whether or not a series converges. As we discussed before, once you know that a series converges, you can get a good approximation with it with the computer. The integral test is a method that allows you to look at just the terms instead of having some expression for the partial sums. So when we look at this, as you'll see when you read the text, the integral test requires that your a sub n's be positive, decreasing, and that they're connected with a continuous function. The reason for this is that the proof that that connects together the integrals and the series as one thing depends on those three facts. Without any one of them, you could actually make a sequence of terms that would have an integral converging and a series diverging or vice versa. Okay, so those requirements are important. You need to make sure that your sequence is a sequence of positive terms, or at least is eventually all positive, that it is decreasing, or at least eventually decreasing, and that it's continuous, or at least continuous after some certain point. Okay. And with regard to that, if you've got those three properties, then if the integral converges, then the series converges. If the integral diverges, then the series diverges. So let's take a brief look at a picture here that will help us see why that would be. So here I have specifically looked at the function 1 over x, but I will share this notebook with you, and you can do the exact same sort of thing with any function. And really, the ability to do it with the notebook isn't the important part, but it helps with the visualization. So I've taken here and defined a function which is just 1 over x. And I did some tricky little bits here. The main things that you'll need to notice is that I've got a value set up for n, and that I had this piece here, these dx's, the length of my interval divided by n. Of course, with the way I've got it set up, those are always going to end up being 1. I did this thing called a linspace that just defines a bunch of points across there. And then I took left endpoints and right endpoints. And so using this sort of thing, I can get a quick plot here of what my function f of x looks like from, looks like about x equals 1 to x equals 11 or 12 or something. It's just kind of to get us a rough idea here. So with a visualization here, if you take that same curve, and my picture here is going to be a little bit chunky, but if I take that same curve and I take all of the left endpoints, so here I've got at x equals 1, x equals 2, and so forth, because that function is decreasing, that means if I draw those boxes, the area of the boxes added up is going to be more than the area of what is under the curve. The same lines, I could go over and look at something with the right endpoints, and I can see that I would have an area that is less than it, less than the area of the graph there. So the notion with that is that because the the summation that you'd get for your partial sums is going to be trapping between it that integral. If the integral goes to infinity, then the larger one of those, which is your infinite sum, has to go to infinity. And if the integral stays bounded, then the part of the summation that is under it also has to stay bounded. So if you've got something like the summation here, and of course, that's going to bring up the same stupid thing every time. Okay, so summation 1 over n, you know that you could connect 1 over n with the function 1 over x. We know that that function is always positive for the values of x that we're thinking of. And because f prime of x is negative 1 over x squared, which is going to be negative, then that means we've got a decreasing function. But then further, because f of x equals 1 over x is continuous for all x greater than 0, we've got all of the conditions that we need to actually apply the integral test. So once we've got that, we just take the integral 1 to infinity of 1 over x dx, which is going to be log x evaluated from 1 to infinity, which is going to be then the log of infinity. I should be super proper here and write the limit as n goes to infinity of the log of n, but you know what I mean. But the log of infinity we're still thinking about is infinity. So since this integral 1 to infinity 1 over x dx diverges, the summation n equals 1 to infinity 1 over n diverges by the integral test. Okay. This is probably going to feel a little bit uncomfortable to y'all for a while, but with regard to giving answers about whether something converges or diverges, we do want you to actually write out your reasoning. You do the work, but then you have to express what that work actually said. This is kind of your introduction to what later math is going to be like after the calculus. There, you spend all your time doing just the reasoning part. So, all right. So with that sort of idea in mind, then we actually have something that we can say that's a fairly large scale thing. And that is that if you have a summation n equals 1 to infinity, 1 over n to some positive power, okay, then if that p is less than 1, the series diverges. And I'm sorry, I needed to say less than or equal to 1, the series diverges. But if that p is greater than 1, the least little bit more, if it is 1.0001, any power that's bigger than 1, the series converges. And the reason for that is that if you take an integral from 1 to infinity of x to the minus p dx, when p is equal to 1, we've got the special case we already looked at there with the logarithm. But if p is not equal to 1, then you know that you'll take your x and you will add 1 to the power, and then you will be dividing by that and plugging in this 1 to infinity. And so when you have 1 over 1 minus p, and this x to the 1 minus p, if p is more than 1, then you've got a positive power of infinity, right? I'm sorry I said that backwards. If you've got p being more than 1, you've got a negative power of infinity, and that would mean that it would give you 0. But if you've got p being greater, p being greater or less than 1, then you've got a positive power, and that would mean that you would get infinity out of it. So, and of course, we'd already handled if p is equal to 1. And then you would plug in the other part and have the minus 1 over 1 minus p, which doesn't actually come into play about affecting the convergence or divergence, but this part here does. Okay. So in general, people tend to refer to this as the p-test. I think that that's a bad choice of things to call it because of having to check things for work, ha ha ha. But we often instead say something about this being a p-series. And when we do comparison tests later on, it's always nice to have something that you can compare series to. If it looks like a p-series, then you'll do things by these comparison tests. Okay. So another, well, I started to say another example, but let me comment instead. The time that you want to use the integral test is if the series that you're dealing with looks like something that you know how to integrate. Things that are these p-series, you know how to integrate them. So you would use the integral test, or you would just cite the p-series if it is a p-series. Now let me show you one that's not quite a p-series, but it's pretty close. And that is a summation n equals 1 to infinity 1 over n squared plus 1. Now, your initial urging there, you might say to yourself, oh, I think that's going to be a p-series because it looks like 1 over n squared. It looks like 1 over n squared. It's not exactly 1 over n squared. Math is a very exact discipline sometimes. So we can't use p-series on this, but we can use the integral test because the function that we'll think about is going to be 1 over x squared plus 1. Because everything involved there is positive, this is positive. And if you check your f prime of x that you get on this, let's see, what do we end up with? Negative 1 times 1 over x squared minus x squared plus 1 squared, and then times the 2x, so you end up with negative 2x over x squared plus 1 quantity squared. And for positive values of x, that's going to be less than 0, so that says this is decreasing. And we can also see above that this is going to be continuous because of the fact that you've got the x squared plus 1 on the bottom. There's no way to make your denominator equal to 0. So we can check to see the integral from 1 to infinity of dx over x squared plus 1. And I knew to do this as an integral test because that is one of my formulas that I've memorized. This is going to be the arctangent of x going from 1 to infinity. And your arctangent of infinity, again, you really think you have a limit, is going to end up being pi over 2. And your arctangent of 1 is going to be pi over 4. So this answer is pi over 4. The actual value doesn't matter. It just matters that it is not infinity. And oops, that says that we can make our conclusion here that summation n equals 1 to infinity 1 over n squared plus 1 converges by integral test. And then we're done with it. Okay. So look for things that are easy to integrate. Sometimes you'll be told, use the integral test here, and the thing that you've got doesn't look like it's easy to integrate. And in which case, you know, you've just got to integrate it, okay? We're always going to be dealing with stuff in here that you can actually do the integration for if it tells you to do the integral test. Maybe it's hard, but you know, as long as you know those integration techniques that you covered in Calc 2, you should be good to go. All right. So next thing we'll be talking about are comparison tests, and I'll talk to you more then.